In the set of real number, there does not exist any value whose square is equal to -1 or -9. If we square any real number, it always gives a positive real number. Both real values or real part of complex number should be equal and imaginary part of complex number should be equal. How we got I square is equal to -1? We know that I is equal to root of -1. When you square on both sides, you will get the value of I square as -1. Hello everyone, a warm welcome to one and all. This is your Shruti ma'am lecturing in Vidhyaashram, the Temple of Excellence, Mysuru. In this session, we are going to study about the set of complex number, also algebra of complex number. Now, what do you mean by complex number? Consider a quadratic equation x square plus 1 is equal to 0 or x square plus 9 is equal to 0. Then, what is the solution for these value of x? So when you solve it, you will get x is equal to or x square is equal to -1, or here you will get x square is equal to -9. In the set of real number, there does not exist any value whose square is equal to -1 or -9. If we square any real number, it always gives a positive real number. Whether you square -3 plus 3 or whether you square -pi plus pi, whatever integer or real value you take, the square of negative real number is always positive. Thus, we does not exist any x whose square is negative. Thus, those numbers cannot be studied under the set of real numbers. That means a square root of a negative real number does not exist in the set of real number. Or we can say that the square of a real number whose value is negative is not a real number. Thus, those numbers are studied under the set of complex number, and the simplest equation we take it as x square plus 1 is equal to -1. Thus, we get here x is equal to square root of -1, and we denote I is equal to square root of -1. Thus, the minimum number under the square root of -1, we use it as I. So, any number inside the square root, if you write it in the form of root of -a, then it can be written as root of -a, which can be written as root a into root of -1, which can be written as root a into I, or we can write it as I root a. Thus, these numbers, we call them as imaginary numbers. We have studied the discriminant value, that is b square minus 4ac, when you are studying the set of quadratic equations. So here, if it is equal to 0, we say that the roots are real and equal. And if it is greater than 0, we say the roots are real and distinct. And if it is less than 0, we say the roots are imaginary. That means they are under the imaginary number, which we study in the set of complex number. Thus, the complex number is of the form z is equal to a plus ib, where a and b are real numbers, and it is defined as the complex number. Here, the value of I square is equal to -1. How we got I square is equal to -1? We know that I is equal to root of -1. When you square on both sides, you will get the value of I square as -1. So, this is how we will define the set of complex number. It is the set of all numbers in the form of a plus ib, where the value of I is equal to root of -1. And here, a and b are real number, but I is not a real number. I is an imaginary number. Hence, a number with I is called as imaginary number. And here, we divide the complex number into two parts, that is real part and imaginary part. Here, a is called as real part of complex number, and it is denoted by real part of z. And ib or b is called as the imaginary part, or any number along with I is called as the imaginary part of the complex number, and it is denoted by imaginary part of z. Suppose we have a number like 2 plus 3i. So let me take it an example of 2 plus 3i. then my real part of z will be equal to 2 and imaginary part of z is equal to 3. Suppose if you have a number like root 3 minus I, then the real part of z can be written as root 3 and imaginary part of z will be equal to minus 1. We cannot write I as an imaginary number. Any number along with I is considered as an imaginary part of a complex number. And we have a complex number which is purely real as well as purely imaginary. What does it mean? So purely real means the imaginary part is 0. That means a complex number will be in the form of a plus I0. Your imaginary part is completely 0. So therefore you will have only the real part. Those numbers are called as complex number, which is purely real numbers. And we have purely imaginary complex number also. Here real part is 0. That means the number will exist in the form of 0 plus I into b. So you have a numbers of this form. So for purely real complex number, we can give an example of 3, root 5, minus 1. These are all purely real complex number. And imaginary complex number, we can write it as 3i, root 7i, 5 by 2i. So here the real part is 0. Therefore, they are called as purely imaginary complex number. Next, we have a zero complex number also. What does it mean, zero complex number? Purely imaginary part means real part of the complex number is 0. And when I say it's a zero complex number, here both real part as well as imaginary part are considered as 0. That's why z is equal to 0 is a complex number where both real and imaginary part of a complex number is 0. And we usually denote it in the form of 0 plus I into 0. The value of a and b is 0, hence the whole complex number is considered as zero complex number. Next, equality of a complex number. Suppose I take one complex number z1 as a plus ib and the another one as z2 as a complex number as c plus id, then I say they are equal if and only if a is equal to c. What is a and c here? They are real part. That is, if real part of z1 is equal to real part of z2 and imaginary part of z1 is equal to imaginary part of z2, then only we say that the two complex number are equal. That is, both real values or real part of complex number should be equal and imaginary part of complex number should be equal. So then only we say that the two complex number are equal. Next we have addition of a complex number or sum of any two complex number. Suppose I take z1 and z2 or two complex number, then how we are going to add it? We will add the real part to real part and imaginary part to imaginary part. Suppose I have a complex number in the form of 2 plus 3i and I need to add it with 1 minus I, then I will add the real part to real part, that is 2 plus 1 and plus I we will take common. What is the imaginary part here? 3. What is the imaginary part here? It is minus 1. So we will get the value as 3 plus I2, or we can write it as 3 plus 2I. Anyhow, after evaluating again, you will get a complex number in the form of a plus ib only. So thus addition is nothing but adding the real part to real part, complex number of imaginary to imaginary part. So now let us study the properties of addition under the complex number. When I say z1 plus z2 here, it is same as z2 plus z1. So see here I have taken an example of 2 plus 3i here. Let me add 1 minus I to 2 plus 3i. So I have interchanged the two complex number and I am adding it. So here I have taken in the form of z1 plus z2. Here I am writing in the form of z2 plus z1. So here real part is added to real part, that is 1 plus 2. Then we will take I, then we will take the imaginary part minus 1 plus 3. So the answer is same 3i2. So both are one and the same. Thus, the addition of two complex number is commutative. That is z1 plus z2 is always equal to z2 plus z1. And also it also satisfy the closure property, that is Z1 plus Z2 also belongs to the set of complex number. Complex number is usually denoted by capital C. So when you add any two complex number, you will again get a complex number, and hence it satisfies closure law as well as commutative law, and it also satisfies the associative law, that is addition of three complex number for all the three complex numbers Z1, Z2 and Z3. It also satisfies the identity property, that is whenever Z1 is added to 0 complex number, that is what is Z1? A plus IB. What is 0 complex number? 0 plus I0. Then A plus 0 is A, IB plus I0 is IB again. You will get Z1 again, or we can simply take it as Z only. So any complex number added to 0 complex number will result with the same complex number. Hence, the complex number under addition satisfies the identity property. Here, 0 is called as the additive identity of a complex number. And the next point is, for every Z, there exists minus Z. So for every Z, there exists minus Z, so that when you add those two, you will get an additive identity. Suppose if you have A plus IB as a Z, then minus Z is nothing but minus A minus IB. So when you add this, you will get the value as 0, which is the additive identity of a complex number. Hence, there exists additive inverse for every complex number. Hence, addition of a complex number satisfies closure law, commutative law, associative law. Additive identity exists. We call 0 as the additive identity. Additive inverse also exists for every complex number. Hence, these are the properties under the addition of complex number. Next, we will take the difference of two complex number. So, when you are taking the difference of two complex number, we will take it in the form of Z1 plus minus Z2. So, minus Z2 is the additive inverse of Z2 here. So, suppose if you are taking a complex number 6 minus 3i minus 2 plus I. So, how to subtract it? We need to subtract the real number with the real number, imaginary number with the imaginary number. So, that's why we can write it as, so 6 minus 3i minus 2 minus into plus minus I. So, 6 minus 2 you will get it as 4, minus 3i minus I you will get it as minus 4i. So, difference of two complex number gives the result like this. So, it is always taken it as Z1 minus Z2, where real part is subtracted to real part and imaginary part to imaginary part. Next, we have multiplication of two complex number. Multiplication of two complex number is same as your binomial product. So, two terms are multiplied in a binomial product way, and we will get the result in the form of AC minus BD plus I into AD plus BC. You can also take this as a property and you can use it while producting any two complex number. So, thus, if you want to multiply any two complex number like 1 plus I or I plus 3, we can also interchange and write. The thing is only the real part exists and imaginary part exists. We can use the binomial product method here, or we can use AC, BD and AD plus BC form here. So, here we can write it as 1 into I plus 3 plus I into I plus 3. Just multiply it. 1 into I plus 3 is I plus 3 only. I into I is I square plus 3i you will get. Then it's again a sum or difference of complex number. So, here I square is nothing but minus 1. The value of I square is minus 1. 3i plus I is 4i. 3 plus I square becomes 3 minus 1. So, therefore, the answer you will get it as 4i plus 2, or you can write it as 2 plus 4i. So, this is how we will multiply any two complex number. Next, we have a properties of two complex numbers. So, when you are multiplying any two complex number, Z1 into Z2 also belongs to the set of complex number, hence it satisfies the closure law. Also, the product of two complex number is commutative. It's satisfied, it is one and the same. So Z1 into Z2 is same as Z2 into Z1. Next, the product is associative for any three complex number Z1, Z2 and Z3. Next, we have multiplicative identity. So for every complex number Z, if we multiply 1, then only we will get Z. So 1 is called as the multiplicative identity of a complex number, and here 1 is purely real complex number because for 1 imaginary part is 0. Suppose you have a plus ib as z and 1 plus I0 as another complex number, then a plus ib gives you the same a plus ib. So thus we have z into 1 is equal to z. So when you're multiplying with 1, which is purely real complex number, any complex number multiplied with 1 gives you the same complex number. Hence here we call 1 as the multiplicative identity of a complex number. Now coming to the inverse, so for every z, 1 by z is considered as the multiplicative inverse, so that it will result as 1, which is the multiplicative identity. And 1 by z is also called as z inverse. We call it as a multiplicative inverse, which we will study later. So here z inverse exists for every complex number which satisfy the property z into z inverse is equal to 1, which gives you the multiplicative identity. Hence, for every complex number z, there exists a multiplicative inverse. Next, we have a division of two complex number. So division of two complex numbers z1 and z2 is nothing but z1 by z2. So here the denominator z2 cannot be equal to 0 complex number. That is, it cannot be equal to 0. So it is same as the product of z1 and inverse of z2, 1 by z2. Next, we have integral power of I. So let's study the powers of I under the complex number. We know that I is equal to root of minus 1. Let me square it on both sides. Then I'll get I square is equal to minus 1. So if I take I cube here, I cube can be written as I square into I. So thus I square is minus 1. Minus 1 into I is minus 1. I minus I here. Next, I'll take I power 4. So I square into I square, which is minus 1 into minus 1 plus 1. Let us go on like that. Let me take I power 5. I power 5 can be taken as I power 4 into 1. So I power 4 into I. I power 4 is 1. 1 into I is I. I power 6, I can write it as I power 4 into I square. I power 4 is 1. I square is minus 1. Minus 1 into 1 is minus 1. I power 7 can be written as I power 4 into I cube, which I will get it as minus I. And I power 8 is I power 4 whole square, which is nothing but 1 again. So for every multiple of 4, the values of I goes on repeating. Hence in general, so for I power 4n or for multiples of 4, the value of I is always 1. So for n multiples of 4 in terms of power, integral power of multiples of 4, I value is always 1. So for 4n plus 1, for 4n it is always 1. So for I power 1 is nothing but I only. So which is nothing but I only. So therefore whose value is root of minus 1. Next we have I power 4n plus 2. I power 4n plus 2 means I power 4n plus I square. So I power 4n into I square. I power 4n value is 1. I square value is minus 1. And I power 4n plus 3 is I power 4n into I cube. I cube value is minus I. So for integral multiples of 4, we will get the value as 1. Thus, the minimum value for which I becomes 1 is 4. And for other numbers in the form of multiples of 4 plus 1, multiples of 4 plus 2, multiples of 4 plus 3, we will get the values like that. So, any number in the integral powers of 5 can be reduced into one of these form, and the value will be from this 4. That is, either it will be 1, root of minus 1 or minus I only. Now let me take an example here. So let me take I to the power 35. So when I say 35, I told you always write the integral power as a sum of nearest multiple of 4 plus some whole number. I know that here the nearest multiple of 4 is 32. So that's why I will write it as I to the power 32 plus 33. And I power 32 is multiple of 4 and I'll separate I cube. I power 32 value is 1 because it's a multiple of 4 and I cube is nothing but minus I. So therefore the value is minus I. Hence any integral power of I can be reduced into simple form as 1 root of minus 1 I or minus I. Some of the standard identities you can use while expanding or solving any two or more complex number. So here are the standard identities for two complex number. It is in a plus b whole square form, a minus b whole square form, a plus b whole cube, a minus b whole cube and a square minus b square form. So in the place of a and b, you have two complex number z1 and z2 and the expansion is one and the same. So important thing to note here, if a is positive real number, I told you a is a real number, but root of minus a is not a real number because we doesn't have a solution as root of minus a in the set of real number. Hence, root of minus a can be written as root a into root of minus 1, which is nothing but your root of minus a. So instead of root of minus 1, we will write I. So therefore, every number as root of minus a can be written as root a I. And we know that root a into root b is equal to root ab under the set of real numbers. So there every a and b is a positive real number or it is a 0. So for all the 0 and positive real number, root a into root b is same as root ab. But for a complex number whose value is less than 0, ab or negative real number, this condition does not satisfy. So let me take a number here. Let me take root of a is less than 0 means I need to take any negative real number. Let me take it as minus 1 into, let me take another negative number minus 2. And here I'll take root of minus 1 into minus 2. So multiply here, what you will get? So here root of minus 1 is I into root of minus 2 can be written as root 2 I. And here it is root of 2. So what is I square? I square is minus 1. So you will get it as I square root 2 is equal to root 2 here. So I square is minus 1. So therefore minus 1 root 2 cannot be equal to root 2. So when you multiply any two numbers or any two negative real numbers using this condition, these two cannot be equal. That is here the left hand side cannot be equal to RHS. This condition is only true for 0 and positive real numbers. So thus for any quadratic equation like x square plus 1 is equal to 0, I said solution will be in the form of plus or minus root of minus 1 where we take root of minus 1 as plus or minus I. So now we need to get here x square is equal to minus 1. So let me check, let me take I here. So here I square is also minus 1. Minus I whole square is nothing but I square. It is also minus 1. Thus, the solution of the quadratic equation x square plus 1 is equal to 0 is plus or minus I. Similarly, x square plus 9 you will get. This implies x square is equal to minus 9. Here the solution is plus or minus 3i. So that's why plus 3i and minus 3i will become the solution for the quadratic equation x square plus 9 is equal to 0. Thus, these are the solution which exist in the set of complex numbers. Now let us take few problems here. So the first one, if 4x plus I into 3x minus y is equal to 3 plus I into minus 6, then find the value of x and y. We know that two complex number are equal only when the real part is equal to the real part and imaginary part is equal to the imaginary part. So let us equate the real part. So here we have 4x is equal to 3 and imaginary part as 3x minus y is equal to minus 6. So here we'll get x is equal to 3 by 4. If I substitute x is equal to 3 by 4 here, so minus 6 can be shifted here, we'll get y. So we will get 9 plus 24 divided by 4 is equal to y. So we will get y is equal to 33 by 4. So this is the value of x and y. Next, express the following in the form of a plus ib. We need to express the following complex number. Either it will be given in the sum, difference, product or quotient form. We need to simplify it and reduce it in the form of a plus ib. Now here we have minus 5i 1 by 8i. So I can get it as minus 5 by 8i square. The value of I square is minus 1. So minus 1 into minus becomes plus. So we'll get that as 5 by 8 and we doesn't have any imaginary part here. So we will write it as 0 into I. So thus we have expressed it in the form of 5 by 8, 0 into I. Or I can write it as 5 by 8 plus I0. A plus IB form. Here imaginary part is 0. You have only the real part. 2 plus I3 plus minus 6 plus I5. So here it will become 2 plus I3 minus 6 plus I5. So 2 minus 6 is minus 4. 3i plus 5i becomes 8i. So this is now value of A is minus 4. Value of B is 8. Next we have I to the power minus 39. So here power is negative. Let me write it in the denominator so that the power becomes positive. Now I power 39 can be written as I to the power 36 into I cube. I to the power 36 into I cube. 36 is the multiple of 4 whose value is 1 and I cube is minus I. So we will get it as 1 by minus I. So I can also rationalize it. So I can multiply I and I here so that I divided by minus I square. I'll get the value of I square is minus 1. Minus 1 into minus become I. Thus the value of I to the power minus 39 is nothing but I, which is root of minus 1 only. Next, 5 plus root 2i divided by 1 minus root 2i. So we have learned the rationalizing of the denominator here. So we can take the conjugate of the given complex number. So that is the second term can be conjugated or the imaginary part can be taken as positive to negative or negative to positive. So let me multiply by 1 plus root 2i divided by 1 plus root 2i. So this is the conjugate of a complex number. So multiplying this, I'll get it as 5 plus 5 root 2i plus root 2i plus 2i square divided by denominator is in the form of a minus b, a plus b, which can be written as a square minus b square. Now the value of I square is minus 1. So 5 plus 5 root 2i plus root 2i becomes 6 root 2i. Here it becomes minus 2. 1 square is 1. Root 2 square is 2. I square is minus 1. Minus 1 into minus becomes plus. So it is 2. Now here you will get it as 3 plus 6 root 2 I divided by 3. So dividing by 3 you will get it as 1 plus 2 root 2i. Now this is in the form of a plus bi. Next we have 1 by 3 plus I7 by 3 plus 4 plus I into 1 by 3 minus of 4 by 3 plus I. So first let us write all the terms which are real here. 1 by 3 plus 4 minus into minus 4 by 3 becomes plus 4 by 3. So this is the real part. Let me take the imaginary part now. So 7 by 3 plus 1 by 3 minus into I is minus 1. So taking LCM as 3 here. So we will get 1 plus 12 plus 4 divided by 3 plus I into 7 plus 1 minus 3 divided by 3. So we will get the value as 17 by 3 plus I into 5 by 3. So thus this is again in the form of A plus IB. So thus, however form they have given, you just need to simplify it and reduce it to the form of A plus IB. So thus in today's session, we have learned what is the set of complex number and the algebra of complex number. We'll meet you in the next session with the new concept. Until then, keep watching, keep learning, keep exploring. Thank you.